It's visible, doctor. Perfect.
Yeah, it's fine.
Yeah, I'll just go ahead with whatever I've gotten.
Right.
Yeah. So, before beginning your talk, let me give a brief overview of your achievements to all the attendees. Good afternoon, everybody. Today we have with us Dr. R. Shrikant, who is an associate professor in the Theoretical Sciences Department of Poornaprajna Institute of Scientific Research. So, Dr. Shrikant will be delivering third talk in the series of quantum series, second quantum series. He has published, he has obtained his PhD from the prestigious Astrophysics Department of Indian Institute of Science, Bangalore. He has published over 110 publications in national and international peer-reviewed journals, and he also serves as a reviewer for several journals. He is one of the editorial board members of the international journal named Quanta. His main areas of research interest are foundations of quantum mechanics, quantum information theory, quantum cryptography, solar physics, and with this brief background, I request Dr. Shrikant to take over and deliver his talk on quantum correlations from weirdness to applications. Over to you, Doctor.
Yeah, thank you very much, sir, for your kind introduction.
And Doctor, 1 minute. I take this opportunity also to welcome Dr. Usha Devi, Madam, who is the chairperson of our Quantum Science and Technology group, and also other senior faculties who have joined here, Dr. Girija, Dr. Girish, Dr. Mohisina, Dr. Raj Kulkarni, Dr. Chandra Kumar, and Dr. Sidraju, and all the participants who have joined both on Cisco WebEx and YouTube platform. For all of you, a hearty welcome to this session. Now, over to you, Dr. Shikha.
Yeah, thank you very much, sir, and also greetings to all of the fellow panelists and student members and faculty members from the respective institutions. I hope you do not mind that I've just used my written notes. There was a computer problem a while back, so I had to scramble quickly together some things for the meeting. So that is the reason it is. But I believe it's overall quite clear to display. So with no further ado, let me just get started. So it all begins, if I may say, about a problem that Einstein and his collaborators had about quantum mechanics because they felt that quantum mechanics was too weird to be true. And there were a series of talks that Einstein, a series of ideas through which Einstein tried to show that there was something wrong with quantum mechanics. Over time, those arguments became refined, and by the end of towards 1935, which is the Einstein-Podolsky-Rosen famous Einstein EPR paper, so they had crystallized their argument whereby they make use of quantum non-locality, which, by the way, was not known by the term at that time, and uncertainty principle to make an argument that quantum mechanics is incomplete. And in the language that Bell later on gave to the argument, the essential argument is quite easy to explain, though there are a lot of conceptual and philosophical ramifications of it which are worth pondering about. In any case, supposing we start with singlet state, which is the down up minus up down, which you might have encountered in your BSc course. But for our purposes, we will basically take it to be the normalized state, which is 0, 1 minus 1, 0. Let this be our state psi. Now, so this particular state, as you can see, if you have Alice holding one particle and Bob holding another particle, and if both of them measure the Pauli X observable, or if both of them measure the Pauli Z observable, they will find anti-correlated results. This is something that we know from our undergrad studies also. So now supposing what Einstein and his co-workers invite us to think is down a slight counterfactual journey, which is to imagine that Alice measures sigma x, let us say, and she obtains +1. Therefore, she is able to predict that if Bob were to measure sigma x, then he would get -1. And in their terminology, therefore, Bob's spin observable Z possesses an element of physical reality. Now, here comes a crucial point that we do not think, or EPR do not think, that Alice's measurement could have actually disturbed the distant particle. Rather, it is the case that it prepossessed the particular value, and Alice's measurement merely allowed her to discover what that value is and infer that value. And they are led down this path of inference because of Einstein's relativity theory. So, Einstein reasoned that this sort of a superluminal disturbance is not allowed by his theory. So, he said that the sigma z value should have been prepossessed by Bob's particle. Alternatively, Alice could have measured sigma x in that case, so she could measure sigma z, and one can make a similar argument that she might, let us say, obtain -1, in which case Bob's particle is left in the state of sigma z being +1 if he were to measure it. Again, Einstein, Podolsky, Rosen invoked the special theory of relativity to rule out that a remote measurement disturbance could have taken place and infer that Alice, she merely discovers a pre-existing value. But this would imply that Bob's particle, you can have a simultaneous reality of sigma x and sigma y. That is to say that sigma x and sigma y can simultaneously possess a definite value, which is counter to Heisenberg's uncertainty principle, which disallows us from measuring or knowing the values of sigma x and sigma z simultaneously. So this is the crux of the EPR argument. So they say that quantum mechanics must be incomplete, and they vaguely present the hope that what we call today as a local realist completion of quantum mechanics should be possible. That is to say that maybe there is a deeper theory than quantum mechanics where all the incompatible yeah, non-commuting observables in quantum mechanics would have definite simultaneous values. So this problem, which was given in 1935, remained so for almost 30 years because people thought that this was more like a philosophical objection by Einstein and his co-workers, and that anybody could choose what we, which side we wanted to side with, whether we accept that quantum mechanics is complete or it's not complete, depending on our own philosophical predisposition. So that seems to have been the state of affairs, which seems quite surprising, of course, in retrospect. And then John Bell came along and he, through a series of thoughts, mainly because he had looked at Bohm's theory of, where he has a realist but non-local theory. So he surmised that Einstein was not, he could guess the sense in which Einstein had got it wrong. And part of the reason why people thought that Einstein was correct because of a result due to von Neumann. So von Neumann, who formulated the first mathematical theory of an abstract mathematical Hilbert space formalism, etc., and the operator algebra. He is the person who set forth for quantum mechanics, and he also supported Einstein. And for this reason, people thought that probably there is a deeper theory to be discovered, etc., and that there is a local realist completion of quantum mechanics. And then Bell, on examining Bohm's theory, which could be characterized as a non-local realist theory, concluded that Einstein was wrong, and his concrete argument could be again explained in a simple way, but which invites a lot of deep thought. And so the idea here is that you have a source lambda which distributes a particle to Bob on who holds the the particle B to Bob and the particle A to Alice. And on the left-hand side, you have Alice who inputs the variable X, a binary variable X, and outputs the variable A. Similarly, Bob on the right-hand side measures, randomly inputs Y, and he outputs the variable B. Again, both the inputs and the outputs are binary. Now I can write down a simple expression which looks like this, which is nothing but A naught plus A1 into B naught and A1. So I just write down some sort of a correlation between the outputs, I mean, between the measurements of Alice and of Bob, which is in this form. It's not difficult to see that if you pre-assign a value to the particles on A and B side, if you assume that the property which is x is equal to 0 and the property corresponding to x equal to 1, if they have definite values of +1 or -1, then this particular inequality, then this expression a naught plus a1, because for example, in a given instance, a naught could be equal to a1, right? So if it's equal to a1, then the second summand will vanish, and therefore I'll have +2, depending on whether it's +1 or -1. On the other hand, if a naught is not equal to a1, then the second summand in the LHS of this expression will be non-vanishing, whereas the first summand will vanish. And therefore, this particular expression can only evaluate to be plus or -2. And taking an average, therefore, I should, if I have a statistical distribution of inputs and various trials in which randomly inputs are assigned and then you find out outputs, if you have these things prepared from a common source, which is lambda, then this value should lie between +2 and -2. Or taking the absolute value, it should be less than 2. We will call this quantity S. And this has been experimentally tested, and we know that quantum mechanics violates this. This is a famous Bell's inequality, which is violated in quantum mechanics, most recently in a spectacular way by an experiment in 2015, where they closed various loopholes. So even when you do these experiments, it is a very complicated thing to rule out any local explanation, and through a series of loopholes, and things like efficiency loophole, the localist loophole, etc. And this experiment is famous because they were able to close down all the three famous loopholes that have been known and which have been plaguing Bell type experiments. And Bell inequality violation can be violated to the maximum, which is called the Tserilson bound of 2√2. If Alice and Bob, for example, share a familiar singlet state, and A naught and A1 will correspond to sigma z and sigma x measurements, and let's B naught, or the choices on Bob's side, will correspond to these two observables. And when we do this, a simple algebraic manipulation tells us that the expectation values in each case will be 1/√2, and therefore this quantity evaluates to 2√2 in quantum mechanics, which exceeds 2. So there were a series of experiments that were done. So when in 2015 Henson's experiment came out, I was wondering if his group would be given a Nobel Prize, considering the gravity of what their achievement is. But I think the Nobel Committee eventually gave a Nobel Prize for the test of violation of Bell's inequality in 2022 to some of the founding fathers in the experimental and theoretical side of this inequality, which is Aspect, Clauser, and Zeilinger. One thing about the inequality that we've talked about, it is a kind of weirdness of quantum mechanics that is exposed through a statistical test. So one has to perform this experiment over a number of rounds and collect the statistics, and then check that it violates the Bell's inequality. And there was a very interesting proposal that was made in 1990 by Greenberger, Horn, and Zeilinger, who demonstrated quantum non-locality without having to make use of any such statistics. And in one shot, you can actually make the, give a demonstration of non-locality. For this, they make use of a 3-qubit state, a 3-particle state, which is the GHZ state, which has this very simple form, as you can see, also called a cat state, which is 000 plus 111. Other states are possible, but this will suffice for our purpose. Now, one can show that, so you have 4 possibilities. That is, Alice and Bob Alice, Bob, and Charlie, these are the 3 people. Each of them can measure sigma x or sigma y. Now, if Alice and Bob, let's say, measure sigma y and Bob measures sigma x, then one can easily check that the expectation value will be -1. So this means that if Alice and Bob both measure, and if Alice measuring sigma y finds +1 and Bob finds -1, then measuring sigma x, Charlie will necessarily find -1, so that the product of all their spins will turn out to be -1. So if you have therefore YYX, it will be -1. Likewise, if it's YXY, it will be -1, and XYY. So these are all, let's say, algebraic identities for this particular state. And you can also check that if XXX is measured, then you get a +1, because applying this operator, the zeros are flipped to 1 and the ones are flipped to 0. So obviously it's +1. Now, this contradicts a local realist explanation for the following reason. Supposing we try to explain this data by saying that in the case of Alice, Bob, and Charlie, in each of their cases, the particles possessed a definite value of +1 or -1, that is the sigma x and the sigma y. Okay, that would mean, for example, so let's look at, I've set these things as a series of rows. So let's look at the first column. We have YY, XX. In the second column, we have YX, YX. In the third column, we have XY, YX. So what's the pattern you find here? So we find that the Y or X happen an even number of times, right? They're repeated to an even number of times. So no matter whether you assign them a +1 or a -1, if you pre-assign a definite value, then multiplying along the columns, you get a +1, +1, and +1. On the other hand, on the right-hand side of these arrow marks, as you can see, I get -1, -1, -1, and a +1, right? Multiplying on the right-hand side, I get a -1, and coming from the left-hand side, I get a +1. So you have a dramatic contradiction in just a one-shot measurement. So what this says is that, again, this is another manifestation of non-locality, and says that you cannot have any local pre-assignment of values to y and x. It is as if when Alice is making a measurement on her particle, if there is an unmeasured particle, it produces, a non-local influence on the outcome of that particle. A further subtlety, of course, is that unfortunately you cannot use this to send any faster than light signal. Yeah, so having talked about non-locality, so that would be, I want to stress at this point that quantum non-locality is the most counterintuitive feature that quantum mechanics can give. We have contextuality, we have entanglement, and we also have the incompatibility of observables. For example, like Heisenberg uncertainty principle, which comes just from the non-commutation. So we have these various aspects, and quantum non-locality, in some sense, takes them to the next level. And we do have this feeling as to what could be the message that nature is trying to convey to us about her essential nature. So while we ponder about this with a sense of mystery, the fact remains also that this weirdness can be harnessed for actual technological applications. As you might all know, we have the threat of a quantum computer. So In a quantum computer, certain calculations can be speeded up, and it turns out that the mechanism through which most of cybersecurity works today can be rendered insecure by the power of a quantum computer. Fortunately, quantum fights quantum. You can use quantum cryptography in specific the idea that you can share secret bits between Alice and Bob using quantum entanglement, and also the fact that you can generate randomness using quantum effects. So these would provide instances where quantum mechanics saves us from the threat of a quantum computer. So I will briefly talk about how quantum non-locality can be used for sharing, secret bits between two stations. So if Alice and Bob share an entangled particle and entangled state, let's say a singlet, and perform local measurements and obtain certain statistics that violates a Bell inequality, it turns out that this could be the basis for sharing a secret key and also for creating randomness. So specifically, you can certify randomness via non-locality. The idea is that non-locality certifies that Alice measurement outputs, the measurement outputs of Alice did not pre-exist. There is no record of the output that Alice produces anywhere in nature, in the whole universe. So it is, in a sense, created ex nihilo, out of nothing. It is completely random. So when they perform a measurement on a singlet, on a non-local state that violates a Bell's inequality, it is as if the outputs that they produce are random. In a sense, the randomness is created on the fly, right? Only when they perform the measurement. There is no record of them anywhere. So the non-locality certifies randomness in a device-independent manner, meaning to say that we need not have made any assumptions about the devices that Alice and Bob used in order to produce these random numbers. So I just want to stress here that that turns out to be one of the most important and fruitful directions of current research, both theoretically and also in technology. Now, in terms of quantification, for example, in this context, randomness or the unpredictability can be quantified by P max. So you have a probability distribution. You can take the largest probability of outcome, and the H-min, the min entropy, is defined as minus log P max. So you have different quantifications of entropy. So this is a particular quantification that is used in terms of in the context of cryptography when you're trying to talk about how insecure it is. So we want to quantify P max of a potential eavesdropper. So the eavesdropper is eavesdropping on our quantum system, and she tries to predict what a particular bit is, right? And to the extent that she is successful, our crypto system is insecure. So Pmax can be used to bound the amount of knowledge that she has. And so you can say that one way to quantify it is, for example, the probability of most uh, probable output given the adversary's knowledge. A recent reference, for example, would be quantum non-locality by Kstacademy. Yeah, now we can define a quantity which is called P guess. So intuitively, P guess is an adversary's ability to guess the value of a secret bit that Alice and Bob are sharing. Right? Ideally, you want it to be half because then Eve has no knowledge. But the greater and greater that P guess is approaching one, the more and more dangerous it is for Alice and Bob. It means that the adversary is able to guess their secret bit to a greater and greater accuracy. On the other hand, the closer and closer it is to the value half, the more and more secure the crypto system is. If it is half, then it means that Eve's ability to guess the shared bit is simply equal to a coin toss. So she is none the wiser. And without going into the details, I just want to give this pretty formula which says that the p guess, that is the probability, the average guessing probability for an adversary, is bounded above by this quantity that is given here. So S is the Bell inequality violation that we had written earlier, the Bell quantity, right? That particular correlation. So Alice and Bob, what they do is they want to share a secret bit, so they could have an experiment where Alice has one half of an entangled part and a singlet, and Bob has another part of the singlet. They could have a number of share a number of such particles. Then they take make use of a sample of a fraction of these particles, and on them they test the Bell's inequality violation. And if they find that the violation observed level of violation is S, then they can use this to upper bound the amount of information that an eavesdropper can eavesdrop on any secret bit that can be extracted out of this entangled system. So they have this system of entangled particles, and beyond that, they don't know. Right? They probably purchased all the measuring devices that they got. All that they know is they perform these measurements almost simultaneously on each of their stations, and they obtain a statistics, and then they check how well the Bell's inequality is violated. So if it is violated sufficiently strongly, then to that extent they can sort of bound upper bound effectively Eve's information. So as you can see, for example, if their Bell inequality violation is just 2, in other words, there is no violation at all. They are pretty much at the best classical bound. They are at the classical bound. So S is equal to 2. Then plugging it into this formula, we find that it is essentially square root of 2 minus 1. And so we see that P guess is nothing but 1. So like I said, if P guess is 1, then it means that Eve, in principle, has full information on the secret bit that Alice and Bob are sharing, and therefore that there is no secrecy at all. So it is an insecure system. And so, I mean, there are two sides of the coin. I will, on the one hand, talk about randomness generation. They are essentially very closely related because pretty much the same kind of experimental setup could be used for generating randomness or for sharing these bits. In the particular configuration that I have put forth here, so they could use this for generating randomness, and by the same setup, pretty much the same setup, this randomness could be shared between Alice and Bob also. On the other hand, notice that if they reach the Cyrilson bound, which is 2 root 2, plugging in that, we find that P guess turns out to be half. So it means that if they're actually able to violate Bell's inequality to its maximum possible quantity, then the secret bit or the randomness that is produced will be perfectly secure. So these considerations actually take us towards the vast and very important and currently relevant in modern times field of device independent quantum key distribution. So as with randomness generation in quantum key distribution, so Alice and Bob sharing a private key, the role of non-locality is basically to lower bound the H-min, the min entropy that would characterize Eve's knowledge of the system. The key difference between randomness generation and key distribution is with respect to distance. It can be minimal if you want to do a randomness generation, meaning that the two entangled particles could be simply within Alice's laboratory because she just wants to generate these two randomness, the particle 1 and the particle 2, as long as Alice ensures that they're measured almost simultaneously, so that any even light speed signal could not have traveled between Alice and Bob, to rule out any kind of localist explanation, then you produce genuine randomness as far as our current knowledge of physics can tell. But if you, in the case of QKD, you have pretty much the same setup, except Alice and Bob can be separated by thousands of kilometers. Of course, because of this, practical issues can be different. So in a QKD setup, you can have channel losses, and so you could have potentially other kind of uh, loopholes. For example, something called the detection loophole, which says that if your efficiency with which you can successfully perform the bell test is not sufficiently high, then you could always use a local realist explanation to cheat and produce the Bell inequality violating statistics. And I'll come to the last topic that I wanted to cover. So what we have talked about now is quantum non-locality. As I said, that it represents in many ways the strangest departure of quantum mechanics from our classical intuition of about what reality is. But there's one thing there, that in the bell type experiments that we spoke about, you always saw that there was multiplicity of inputs. So you need the free will of Alice, that free will of Alice and Bob, so called what I would call as free will, but sometimes it is more formally called as measurement independence, meaning to say that the measurements that Alice and Bob make should be uncorrelated with the underlying state. But with quantum networks, it turns out it sort of uh, flies in the face of that particular expectation that we have, that fundamental to non-locality is that the experimentalist must possess free will. To see the importance of this, imagine that there is a movie which is made of, let's say, Anton Zeilinger. There is an actor who plays Anton Zeilinger, and the whole screenplay will already tell what tests they make and whether they will get, what are the outcomes that they go into. The inputs and the outcomes are all predetermined by the screenplay that is there in the movie script. So in this case, you can think of it as a Bell inequality violation without free will, because each of the actors simply plays the role that the screen script is asking them to. And so as you can see, of course, you can trivially violate uh, quantum non-locality. I mean, you can reproduce quantum non-locality by a purely local explanation if you remove free will. So the fact that you have multiplicity of choice on Alice's side and Bob's side, and that these experimentalists have the freedom to make a choice regarding what measurement they will make, is quite crucial to demonstrating quantum non-locality. So it came as a great surprise that you can demonstrate quantum non-locality even without having to have Alice and Bob to possess free will. And that came up recently for the last few years, which when people have looked at causal networks, or you have a network of users who perform measurements, obtain outputs, and we then produce what is a local model and then show that quantum correlation is violated. So in this context of quantum networks, the entanglement is distributed from independent sources across the network. So you have on the vertices, you have observers who will perform measurements without inputs, meaning to say that they will perform only a fixed measurement. But the crucial point is that they perform entangled measurements without multiplicity of inputs. And this will be found to lead to a novel type of non-locality that goes beyond the Bell type of non-locality that we've been talking about, which is a departure from the hidden variable, local hidden variable model. So, what is the source of non-locality in these novel particles? It turns out that the non-locality actually comes from the entangled measurement itself. So that it is a kind of non-locality which is responsible for the reason that the correlations in network inequalities can go beyond the local model. Here it is worth going back way back to 1994 when the first idea about the power of entangled measurements came up, and this is in what might be familiar to some of you, which is quantum teleportation. To those of you to whom this term is new, I want to say that this teleportation is not like the one that you encounter in the famous Star Wars movies, but nevertheless, teleportation in a present context, I think, is fascinating in its own right. So here what you have is you have Alice and then you have Bob who share an entangled channel and who are able to communicate with each other, let's say using a mobile phone, which is a classical channel. And the problem they have is that an unknown state psi should be transmitted from Alice to Bob. But we will do it through a disembodied process, meaning to say that the state or the qubit quantum particle holding the state will not be physically transmitted from Alice to Bob. Instead, Alice will simply perform a local measurement and then pick up her phone and give certain instructions to Bob. And lo and behold, Bob will be able to reconstruct that state on his side. And through, in the same manner as the teleportation in Star Wars, or I'm sorry, I think I wrote the wrong word, not Star Wars, it's Star Trek. As in Star Trek, you will find that the original copy of the state is destroyed in the sending station. And again, for it, we use a Bell state, which conveniently could be the state 00 plus 11 by root 2. And it is simple to see how teleportation works out. So you have this unknown state, which is alpha 0 plus beta 1. And then you have this Bell state. So I can just re-express the first two particles. So the first unknown, first particle is with Alice, and the first half of the singlet, I mean, of the Bell state is also with Alice. So what she is going to do is she will measure the two particles with her in the Bell state basis. To see what the outcome is, notice that I can just rewrite this expression in the way that I've written it in the second line, where the alphas are simply distributed over the entangled state. And then I can rewrite, for example, the state 0, ket 0, 0, right, as the sum of these two Bell states, which have parity 0. Again, I'm just manipulating all these expressions. So with this simple algebraic manipulation, I can bring it into that last blue colored line below. I'm sorry, I should have put equation numbers, but I sort of forgot to do that. And we have it in the last form. So what does this last equation tell? It means that if Alice performs a Bell state measurement on this system, so that is what I mean by an entangled measurement, meaning to say that the measurement outcomes will correspond to entangled states. So if she obtains the Bell state, which is written as 5 plus, the expressions for which I've given in this black ink matter below, what are these Bell states? If she gets 5 plus, then the original state intact is left with Bob. Whereas if she gets any of the other Bell states, then the original state is left intact with Bob, modulo uh, a local rotation on Bob's side. But importantly, what rotation it should be can be determined by Alice by looking at her own outcome. So she picks up the mobile phone and tells Bob to perform the corresponding rotation. Bob performs that rotation and he is able to recover that state. So, as promised, you have this situation that just by local measurements on Alice's side, she is able to allow Bob to recreate the unknown state which earlier was there with, I'm sorry, allows Bob to recreate the state that was earlier there with Alice. So the moral of this short story is that there is another kind of non-locality which is present also in entangled measurements, and we can think of these network non-locality as essentially arising from that, because as I said, you don't have, there are no inputs to each of the vertices, right? The people who make the measurements do so without any input. So in the case of Bell local hidden variable scenarios, that is the Bell scenarios that we were discussing earlier, also we have familiar algorithms in order to characterize them, because these correlations turn out to be convex, meaning to say that if certain extreme points are characterized, then you can characterize the full set. And the facets of these extreme points, the boundaries of them will correspond to Bell inequality. So in this way, life becomes simple when we try to, I mean, relatively simple, of course, when we characterize them. But here, this it is harder because this problem is not convex, so we are not able to find out any simple characterization. As a matter of fact, even the example I'm going to tell you, I find that there is no definitive proof that it is actually non-local. So that's a bit strange. And in a sense, it tells us how difficult the problem is, but there is increasing evidence based partly on statistical tests, certain analytical results, and even machine learning has been applied. We believe that the state that I will just talk to you about is indeed non-local in the network sense. So, having told what could be the source of non-locality in the network non-local context, so we can go ahead and let me write down the exact model that we are talking about. So, on the left-hand side, as you can see, you have a source, and this is the familiar Bell local hidden variable model. You have the source that distributes a particle to Alice and one to Bob, the input X, and then there's an output A. And similarly, on Bob's side, you go this input and output. So the local model in the standard Bell scenario is the one that I've written here. That you have the lambda and the input of Alice, which will determine her output, and then you average over all possible source settings, the hidden variable that you have lambda. Now, the corresponding situation in the case of a network inequality would be, now when you have a Bell inequality violation, you essentially produce a probability distribution that cannot be written like this. So when you violate a Bell's inequality, you're saying that the statistics or the probabilities that you're getting are too strongly correlated to be explainable in this way. That is, any correlation that you can establish by producing it from a pre-shared source is not strong enough to explain the violation that you find in Bell's inequality. The corresponding picture in this case is the following. So in a triangular case, you have these three vertices A, B, and C. So you have these edges. On each of these edges, let's say you have a source which is alpha, beta, and gamma. So alpha distributes a particle to A and B, the vertices, and beta supplies a particle to A and C, and similarly for alpha. And in this case, the triangle network local, model that you have would be PABC. Notice that on the Bell, this thing you have AB given XY. So there's no such thing here because there's no multiplicity of inputs, and you again have the averaging over the source, right? The P alpha, P beta, P gamma, where I put the subscripts here to indicate that their functional forms may be different. And so we have A given beta and gamma. Is that right? Because if you look at A, it has contributions from gamma and beta. So my local model essentially says that it has some shared randomness, for example, coming from gamma. And therefore, the output that is given here will depend on the input that comes through gamma and beta. So that is what has been told here. And therefore, the challenge here in the case of network inequality is to produce a correlation and show that it cannot be written in this way. So such a distribution will lack a classical explanation in the sense of equation 1 that I wrote, and such a state will then be called triangle non-local. And now, a very specific instance where this has been shown is, let's say we have the four possible outputs given by 0, 1, 2, and 3, right? Because we imagine that if we are doing a quantum experiment, from each of the sources, you have a two-dimensional particle coming in the most minimal sense. And therefore, you have 2 into 2, which is 4 possibilities. So let's label them 0, 1, 2 and 3, and one such distribution which cannot be, which apparently as far as all the evidence today is concerned, cannot be written in that network local form, is a distribution which has been called the elegant distribution, which has this very innocuous form, which is that if the outputs A, B, C are equal, let's say the with the probability which is 25 by 256, and if all of them are unequal to each other with probability 5 by 256, if two of them are equal and they are unequal to the third one with probability 156, so you can check that they're all normalized. So when you go over all the permutations, then you find that the probability sums up to 1. So if we have this so-called elegant distribution that is produced, in the measurements at each vertices, then this turns out to be network non-local. And there are good numerical and analytic evidence that this PE is indeed triangle non-local. So here and then we have an instance of a new kind of non-locality. So one that requires multiplicity of inputs and has a bell type of non-locality, which essentially the message there is that the inputs that Alice chooses seems to influence the output of Bob. So that's the kind of causal picture that you can have. And on this case here, you have a non-locality comes because of an inherent non-locality in entangled measurements. Now, this particular state can be given the statistics can be produced, of course. This is well known and it is a fairly straightforward calculation. Again, our familiar singlet state can be shared along each of the edges, and the measurements, fixed measurements that Alice, Bob, and Charlie will make is given in the following basis. So you have this eta 1, I'm sorry, so you can take it to be, I mean, four possibilities. I've written it as 1, 2, 3, 4 here, and earlier as 0, 1, 2, 3. It doesn't matter. So basically, you have this basis of four entangled states. So they must perform measurements in these entangled states, which are given by this prescription, where the MI turn out to be connected to, you inscribe a tetrahedron in a block sphere. So you get four directions. The MI are determined by that. Then these single qubit states are used to construct that entangled basis. And when you perform measurements on those, then you produce the statistics corresponding to the elegant distribution. And I did see a paper that has recently done it on a photonic platform, Wang et al., which is not yet published, but it seems to be good and it's been put on the archive. So, in concluding, I want to say that quantum correlations present the most dramatic departure of quantum mechanics from our classical intuition about the nature of physical reality. And I didn't have time to talk about various aspects of them, such as contextuality and entanglement, but together, all of these things are the cornerstones of this departure of quantum weirdness, if you like, from our classical intuition. But they're not merely weird curiosities, but they have practical applications at the very heart of tomorrow's technological landscape. So So with these words, I thank you very much. Take any questions. Is it too long or too short?
No, sir. Thank you very much, Doctor. It was really very good and appropriate. I'm sure students would get a lot of take-home message from your talk. Many have joined on YouTube also. You will be highly benefited by your talk. Now we have with us Dr. Srinath and Dr. Anant. This and I request Dr. Srinath sir for his comments. Over to you, Dr. Srinath.
Thank you, Ramesh ji. It was a quite a exhaustive handwritten presentation, and I was fortunate enough to listen to Shrikant ji, and it was an lucid presentation on quantum physics, many topics of the field. Congratulations to Shrikant sir, and hope I think many people may know that he's one of the pioneer in quantum physics, who was in even RRI days, and now he is in Poornaprajna. Many students may get benefit out of his presentation. Of course, Usha madam, Shrikant, and many students used to work together. That's we used to listen about them. Today, we're fortunate enough to listen to Shrikant ji. Sir, thank you, sir, for a nice presentation.
Thank you, sir.
Thank you, Doctor. Now, Dr. Anant. Anant. Well, Doctor, there are a few questions.
Sure.
My colleague, Mr. Umesh, will be reading out them. Over to you, Umesh.
Yes, sir. Can weak measurements reveal more quantumness about the state, sir?
Could you please repeat it? Sorry. Yeah.
Can weak measurements reveal more quantumness about the state?
Yeah, it indeed brings forth a very new aspect. I have not touched upon that here, but indeed it brings forth another, sort of element of surprise within quantum mechanics. And so, because if you expect what the variance should be for certain measurements, and you expect an anomalously greater variance coming because of weak measurements, so that does bring certain new aspects to the whole thing. So here mainly I focused only on how our expectation, basic classical intuition, is belied by quantum correlations. But yes, one can refine and make specific statements by making use of weak measurements. Indeed, yes.
Umesh.
What is the strong measurement limit? Limit the extra quantum correlation value, sir.
Oh, okay. So I think you mean the strong limit, how strong quantum correlations can go will be 2√2. So this is called the Tsirelsen bound, and depending on the algebra of that expression that you're using, you can specify how much it depends on the algebra of the operators. You can show that it is 2√2, and the particular setup that I gave you, example I gave you, reaches 2√2. But now you can also ask the question, is this the one that is the maximum value that is algebraically possible? That turns out to be not the case. That is, you can go all the way up to 4, and one can write down something called Popescu-Roerlich boxes, which can go beyond 2√2 and reach the value 4. So, and they're completely non-signaling. So the idea, I mean, the motivation for this was to try to understand why quantum mechanics goes only up to the strength of quantum correlations allows a violation that goes up to 2√2 only, and does not exceed it. So this has been another fruitful line of thought to understand what is special about quantum mechanics. But a brief answer to your question is that the strength of the correlation need not be the strongest that we can conceive. We can go all the way to the algebraic maximum of 4 also.
Thank you, sir. Sir, how entanglement-based quantum of random number is verified, sir?
Yeah, okay, yeah. So, yeah, this is, of course, a very relevant question in terms of how you want to make use of, entanglement for randomness generation. It's completely relevant, like I said, from a technological perspective, because two of the applications I've talked about are, one is key generation and one is randomness generation. So you can think of this Bell inequality violation that I spoke to you about as kind of certifying the existence of entanglement. So entanglement is kind of a weaker requirement than non-locality. So if you're demonstrating non-locality, you indeed have entanglement in the picture. So you have an underlying entangled state, and it is that entanglement as certified by non-locality that allows you to produce random numbers. Now, if you take care that the experimental conditions under which the violation was observed, right? Like for example, the measurements should be almost simultaneous on Alice's side and Bob's side, and they should be sufficiently far and so on and so forth. These are the matters of closing the loopholes. Then you can argue that the random numbers, there was no record of the random numbers, because if you say that the a random number record existed anywhere in the universe, then Bell's inequality violation tells you that you cannot have distributed from a source. So the only other way is that you should have had faster than light communication for sharing the randomness this way. And so by measuring them almost simultaneously and invoking relativity theory, you are able to argue that these two possibilities are ruled out. So the randomness is genuine. So that is the basic, intuition behind saying that, you can certify randomness through non-locality or entanglement.
Thank you very much, sir. There is one more question, and I request participants, if there are any other questions, please raise your virtual hand so that I can unmute you and you can speak directly to the sir. Sir, NIST 80 and NIST 22 is enough to verify the simulated random number, or else any other test need to do?
Oh, okay. You mean the NIST suite of tests for
Yes, sir.
randomness testing? Oh, yeah. So this is, of course, a very important suite of tests, and but I would say that demonstrating randomness is actually an uncomputable problem in a very deep mathematical sense. So, at the same level, like you can say Gödel's incompleteness theorem. So you can, therefore, what NIST does is it has these clever algorithms, which I would say that with increasing certainty, you can rule out that there is no pattern in your data. And it's a very standard thing. So if you have a quantum technology company that purports to produce, randomness through whatever their entanglement setup or their quantum setup, then they would necessarily have to go and get it tested in NIST. That would be a basic benchmark that they have to do. But if you ask whether one test is really covering it, I mean, I'm sure it could be the best test around, but nothing can really cover it, because you random, except if you have faith in the laws of physics and say that through Bell inequality violation you produce this randomness. On faith, you can take that it is random. But mathematically speaking, randomness is uncomputable. So in a sense, it's unprovable. If there is a pattern, right, I can always demonstrate a pattern and say that something is not random. But how do I prove that? I mean, there is no countably infinite way to prove that there is no pattern in a given data. I mean, so yeah. Of course, I mean, I'm assuming that the data can be unbounded. If you have a finite data, then that's a different matter. Yeah.
Thank you very much, sir. That's it. Sir, over to you, sir.
Thank you, doctors. If there are no questions, I would like to thank Dr. R. Shrikant, Associate Professor, Poornaprajna Institute of Scientific Research, immensely for his very informative and scholarly talk. Thank you very much, Doctor.
Thank you, sir. Thanks a lot. Thank you, everybody.
I also thank Dr. Srinath and Dr. Anant Naik, Dr. Usha Madam for joining this talk. Senior faculties, Dr. Girija, Dr. Girish, Dr. Moisin, Dr. Raj Kulkarni, Dr. Chandrakumar, Dr. Sidraju, Dr. Midun Lal, Dr. Vinay, Dr. Zina also have joined. On behalf of all of us, thank you very much. Tomorrow we'll be having a talk by Dr. Anil Prabhakar, Professor in the Department of Electrical Engineering, Indian Institute of Technology, Madras. We'll be speaking on translating quantum technologies or national quantum mission. So this is a very important topic. Tomorrow you can understand what all are there in quantum mission, probably research opportunities that are provided also could be understood by this talk. I request all of you to join by 3:20 p.m. so that at 3:30 we can start the talk and finish by 4:45. With this, I thank all of you, all the participants who have joined on Cisco WebEx and YouTube platform, and also my colleague Dr. Umesh Gatki for coordinating this program. Thank you very much.
Thank you, everybody.